Hi, Marcus. Thank you very much for the kind introduction, for the invitation. Hi, everybody. I'm Richard. I'm from Linz. Linz is a city that you might know by passing through it by train. So whenever you go to Munich or Salzburg, Linz is on the way. This is kind of like where we are based. It's not so far. It's a kind of like a nice mid-sized city. And I'm really happy about this workshop. Thank you to the organizers for making this happen, because as far as I understand, this is really meant to bridge the gap between kind of like harmonic analysis, mathematics, and maybe what you would consider applications, which kind of like maybe we would still consider as theory in quantum computing or quantum many-body physics. And I want to take this to heart, and I want to spend most of my talk actually to motivate one of the most basic problems in quantum many-body physics, the so-called ground state problem. So if nothing else, I hope that that my talk will help you to understand your physics colleagues a bit better in the future. And I really want to kind of like take quite some time to motivate this, present the ground state problem in a mathematical framework, and tell you what physics jargon actually means. Okay, so this is kind of like one of my main goals for today, to also help you build bridges. And in order for me to be successful, I would really appreciate it if you ask questions immediately. I really want to take everybody of you with me on a journey. And my experience is, if something is unclear to you, it's also unclear to at least 10 other people. And if you stop me and ask, you give me the chance of clarifying and kind of like getting you kind of like back on track. Okay, so questions are welcome. The title of my talk has a lot of physics jargon, learning to predict ground state properties of gapped Hamiltonians. In the first part of the talk, I will tell you what this means. It's essentially a problem about learning features of very high dimensional matrices that are defined, kind of like have latent structure in the sense that they don't have that many degrees of freedom. Okay, so think about latent structures in matrices, but maybe a bit differently than what you usually have in inverse problems. And kind of like the work I want to present today also says something about learning, machine learning, statistical learning theory. And it is an older work, joint work of myself and many amazing, nice and smart people, most notably Robert Küng, who is now young faculty at Caltech, Giacomo Torlai at Amazon Web Services. So here we're going really towards applications. Victor Albert at NIST Maryland, and John Preskill at Caltech. Okay, so these are kind of like more quantum physicists. But what I want to tell you is I want to kind of like first motivate this ground state problem, and then make a provable statement about the possibility of using statistical learning theory to solve these types of latent structure problems. And I want to actually go through the main proof ideas. In fact, the proof ideas will consist of 3 parts, and each of these parts is easy for experts. But when you put it together, you have kind of like a statistical learning, machine learning result about an important problem in quantum many-body physics. And the 3 kind of like, the 3 basic kind of like ingredients is what I thought basic signal processing, but I learned maybe it's not so basic, but this will be easy for Mario, for example. And then some statements about mathematical physics and spectral gaps, which will be easy for David, for example. And then some data compression results about matrix sketching. Where are the matrix sketching experts here? Maybe Mario again. So, and I really want to put an emphasis of intuition and kind of like combining techniques rather than building new ones. And if I did my job completely correctly, you will all be utterly unimpressed by the end of my talk. Okay? So here is the motivation that I already alluded to. What is the ground state problem in quantum many-body physics? Oh, there's a lot of jargon here to unpack. And this is kind of like the central problem of today's lecture. And I actually wrote it down here on the right as a cheat sheet for you. Kind of like, what is a Hamiltonian? A Hamiltonian is a big Hermitian matrix. And it has some physical meaning. It encodes energy. Kind of like energy of a physical system, but in math terms, it's just a big D by D matrix. And big D is very large. If this is a matrix and it encodes energy, the eigenvalues and eigenvectors carry interesting information. And in physics, the smallest eigenvalue is a very interesting one, because if the matrix encodes energy, the smallest eigenvalue is the smallest energy achievable. This is what ground state means. Ground state energy is kind of like the smallest eigenvalue. And the ground state vector is the smallest eigenvector that achieves this eigenvalue. Because the matrix is Hermitian, we know it is diagonalizable, we know that all the eigenvalues are real valued, so we can order them. And the smallest one is the interesting one. Kind of like in math of data science, yes? No. A Hermitian matrix? Yes, yes. Yes. Well, I will talk about the structure later, but short answer, yes. But it's still kind of like a diagonalization problem. So it's kind of like an eigenvalue problem, and the eigenvectors of a Hermitian matrix are basis independent, right? That's it? Yes, to come from physics to the matrix representation. Yes, you're right. Yes, I make a conscious decision here, and I will explain it later. Thank you. You're right, of course. Okay, so the ground state is the vector achieving the smallest eigenvalue. It's the eigenvector with the smallest eigenvalue. This is now a big d-dimensional vector. And then we can look at features, at properties of this ground state vector. And they are basically quadratic forms. And I wrote them down here. So kind of like the smallest eigenvector is something that tells you about the physical system at the smallest possible energy. And then we can try to find features. Because if D is very, very large, we cannot afford to write down all the components of the vector. And we might want to find summary parameters. Okay? And these are kind of like, let's say, polynomial or quadratic functions in this vector. And they really encode physical properties like magnetization, for instance, or correlations in quantum many-body systems. Okay? So far, a lot of jargon, but it's just an eigenvalue problem. Nothing fundamentally difficult here. What makes it difficult is that in the context where this problem arises, with the choice of basis I choose, these matrices are huge. They encode, if we have kind of like a combination of many small, simple systems, then kind of like the laws of quantum mechanics in quantum many-body physics tell us that this Hamiltonian is a 2 to the n by 2 to the n matrix. And if n is 10, this is not scary, it's 1024 by 1024, easy. If n is 1000, which can easily happen because 1000 particles is not that much, 2 to the 1000 is way beyond what we can compute. The ground state problem is not intrinsically difficult, it suffers from a curse of dimensionality. But in quantum many-body physics, and this is why I kind of like emphasized quantum many-body physics so much, the Hamiltonian is not structureless. Kind of like if this were a generic D by D matrix, we would be out of luck, right? Kind of like diagonalizing a generic D by D matrix with Gauss elimination requires, let's say, at least order D to the cube many iterations. Yes? But in the ground state problem, there's additional structure that you could call as maybe choosing a basis. Okay, because like these big matrices are not arbitrary. They only have kind of like a polynomial or logarithmic number of degrees of freedom. Yes, this is something you can, both is possible, but this is something in the easiest case you choose it. Yes. Yes. No, we usually kind of like, for the scope of today's talk, let's fix it. Yes. Yes, it has to be Hermitian. It has the same structure as the Hamiltonian. Thank you, Hans. Okay, and kind of like in this quantum many-body physics contest, there's a lot of additional latent structure. And the latent structure is not the structure you're usually familiar with when you think about kind of like latent structure in matrices, where we think about subspaces and direct sums. The latent structure manifests itself in Kronecker products. And I hope you remember the Kronecker product. If you don't, I wrote it down here. It's a way of taking two matrices and multiplying them to produce one bigger matrix. And the idea is kind of like this recursive block diagonal structure. I have two matrices, and if I build the Kronecker product, I take kind of like the first coefficient of the first matrix, this is a number, and multiply it with the entire second matrix and put it here. And then I make more and more blocks and build up a bigger matrix. If the original two matrices were small d and big D, then the new matrix is D times D. I don't know where the light is. Thank you. Okay, so kind of like this is the definition of a Kronecker product, and it takes small matrices and blows them up to become large matrices, but very, very structured large matrices, because the new matrix has kind of like a lot more degrees of freedom, but it is actually specified by a list of two much smaller matrices. Yes, yes, thank you, Han. Perfect example. I will use that in the future. Exactly. Okay. And the matrices we use as elementary building blocks for these Kronecker products are also very, very structured and easy and 2 by 2. It's kind of like these Pauli matrices. Identity matrix, Pauli X, which is kind of like the negation gate, kind of like then a one with complex numbers, and then a Pauli Z matrix. And they are also, I think, related to the two-dimensional Fourier transform. Okay, so kind of like we have a lot of elementary 2 by 2 matrices. And now I can tell you how we built these big matrices. We built them by adding up elementary Kronecker products of these small guys. Okay? So this big Hamiltonian is promised to be a sum of only logarithmically many elementary Kronecker products of Pauli matrices. Okay? Kind of like a bit similar to having a low rank matrix, where we would have kind of like a sum of very few outer products. But here we have Kronecker products. And this means there's latent structure. Because if I want to store a description of this big matrix, I only need to store the kind of like the lists of the individual 2 by 2 matrices that I use to build up the Kronecker product. Okay. And so the big question in quantum many-body physics, and it's actually one of the most fundamental questions in this branch of physics, is what if we have these highly structured Kronecker product sums of very simple Pauli matrices? Can we learn or say something about the associated ground state energies in the sense that I told you before? Because this is now a latent structure problem. The number of degrees of freedom I need to specify one of these big matrices only scales logarithmic in the big dimension. Yes? Oh. Where does this come from now? Yeah. Because this is important. Yeah. Okay. Because I'm not done yet. This is kind of like the math description. What physicists then do is they use a graphical notation to actually write down how these terms look like. And the way they do that is with a connectivity graph. Kind of like we have n particles. These are kind of like n 2 by 2 systems. This is kind of like the number of Kronecker products we have. And then each of these elementary Kronecker products represents a coupling or a connection between two of these objects. Okay? So for example here, this is an example of 25, n equals 25, so 25 two-level systems. The total dimension of the Hamiltonian is 2 to the 25. This is a big number. Not easy to kind of like solve the ground state problem there anymore. But this connectivity graph tells you or encodes how these sums actually look like. And here you can see that there's a small connection between particle 1 and 2. And this is kind of smallish. And this tells you that there's a Kronecker product that has, let's say, a Pauli matrix X, Y, or Z on the first term, a Pauli matrix X, Y, or Z on the second term, and identities everywhere else. So this matrix, for example, looks like a very, very sparse matrix, where we say kind of like we have a non-trivial coupling for the first guy. This is why we have an X here. We have a non-trivial coupling for the second guy. This is why we have an X here. But we have no non-trivial actions on the remaining systems. This edge here only affects 1 and 2 and nothing else. So this encodes a Kronecker product of a non-trivial Pauli matrix at the first position, a non-trivial Pauli matrix at the second position, and identity matrices everywhere else. Okay? So this is just a graphical representation of the list here. And typically, you only have interactions between two of these objects. So not only are these elementary Kronecker products, but at most two of them are different from the identity matrix. Okay? And if I now think about a general graph that connects n vertices, then kind of like the number of different, now Mario, can you answer your question? The number of different connections is at most n squared, and that's log squared. So I should have a log squared here. Okay? But what this really tells you is kind of like which of these systems get non-trivial Pauli matrices to begin with, and the size of this kind of like connection tells you how large the coefficients in front of these Kronecker products. Okay? It takes some getting used to, but this is really just a graphical representation of a list of these elementary Kronecker products that ensures that the total number of terms is at most log squared of the big dimension, most n squared, and the individual items are not encoded as list elements, but in this kind of like graphical notation. Yes, Hans. Yes. There's coefficients here. Okay? And the coefficients are kind of like the strength here. And what this really means is that kind of like here we see that there's a connection between 1 and 2. And so we would have, for example, an x here and an x here and then identities everywhere else. And there's no connection between 1 and 3, but there's a connection between 1 and 6. And so this would mean we have a Kronecker x on the first guy, identities on guys 2 to 5, another Pauli x on the sixth guy, and then identities again. No. Not in this graph. Yes. In general, you have a connectivity graph that tells you kind of like which two of them are related, and this is a particularly easy graph that forms a lattice. Okay? Thank you very much. And here in this concrete case, the actual Hamiltonian looks kind of like not, it's very structured. It has kind of like these coefficients. And it's kind of like the thickness of these lines. And whenever there's a line, we have Pauli X connections, Pauli Y connections, and Pauli Z connections. So each of these lines is actually stands for 3 of these Kronecker products here. One with Pauli X, one with Pauli Y, one with Pauli Z. Okay? And just to do parameter counting, here we have 25 of these elementary Kronecker spaces. So we have, let's say, 10 million dimensions. E is 2 to the 25. And the number of degrees of freedom we have is only 40. Because there's only 40 of these connections where we can choose the strength. It's latent structure. Kind of like 40 degrees of freedom embedded in a 10 million by 10 million matrix. The question is now, can we say something about the smallest eigenvectors associated with these matrices? This is the ground state problem in quantum many-body physics. Is there questions or comments at this point? Yes. 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 This is typically the problem description. I will talk more about that later. But what quantum many-body physicists actually do is they look at different choices of these couplings and then want to analyze the features of the smallest eigenvectors. This is what you do when you, for example, study quantum materials, actually. Kind of like choosing these J's is kind of like an important task, and it's kind of like the specification of the associated problem. And this is really something to do with magnetism and superconductivity. So kind of like this is where kind of like the physicists start to jump in. Excellent question. More questions or comments? Yes. No, a tensor network is an approach, I will talk about this later, to solve the ground state problem. This is just the definition of the problem, and tensor networks are the solution. And tensor networks really, they use the Kronecker structure as well. This is kind of like where these Kronecker structures come from. Excellent instinct. More questions or comments? Yes. Well, this is kind of like, I'm not so good in physics, but a general physics principle, yeah, you laugh, but it's actually true. A general physical system is the kind of like systems try to cool down to the ground state energy, and this is kind of like a stationary distribution. Yes? I mean, this is an interesting question, but a very interesting question is kind of like really think about this as trying to build up a new material. Kind of like there you can engineer these connections, and you maybe want to do something cool, like a magnet or a superconductor. And then what you would want to do is that kind of like these features exist in kind of like the stationary state of your quantum material. And so you would first kind of like tune it, then you would cool it down, and then you would analyze the features kind of like in this configuration. And the ground state features exactly tell you that. Kind of like something about magnetization or conductivity. These are really features of the ground state distribution because this is a stationary distribution. Yes, yes. Yes. Pardon? Yes. No. Sorry, this just means that kind of like, it's kind of like when I cool down, it's kind of like the optimum. I cannot go further. Kind of like the solution to the optimization problem of minimizing its energy. Okay, thank you for keeping me honest. More questions or comments? Okay. So this is at least my attempt of explaining what the ground state problem in quantum many-body physics is to a more math-inclined audience. It's about huge matrices with a lot of latent structure with very few degrees of freedom, but it's not the typical sums of outer products that we have in low rank, but it's Kronecker products. Yes? Yes. 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 This O, can I use the next slide to kind of like try to motivate this? This is something that actually kind of like you choose. This could represent physical observables, but it's also very important for the machine learning model I want to talk about. I think so, David. What do you think? Thank you, David. Okay, I guess now I have kind of like the problem well defined. Thanks for being so interactive. Let me now talk about the vision and also a caricature of what our colleagues in condensed matter physics departments do, and there's a lot of them. Okay, so kind of like the high level vision, what I try to convey to you is that kind of like these Hamiltonians, these energy functions, are very, very high dimensional objects, big matrices, but they are represented by a succinct string of information. Kind of like, although they are very, very big, I can always write them as a sum of very simple terms. And if I want to store it, the number of bits I need to store only scales polynomial in the number of particles, at most quadratically. Okay? And now this is why I want to talk about the observables. Somehow you want to learn about the smallest eigenvector of these big matrices. And the easiest way to formulate this problem is tell me the smallest eigenvector of this problem, right? But now, as an algorithm designer, I have a problem because the smallest eigenvector is a very, very large vector. It has d entries. And when I really want to kind of like, how should I receive this vector? Do I really expect a list of 2 to the 1,000 entries? This doesn't work. I want to find an efficient algorithm. And if I want to do efficient algorithm design, I have to make sure that the input only scales polynomially in problem size, and the output also only scales polynomially in problem size. And this is why I insist on these observables. Like many physicists really want to find the ground state, a classical representation of this smallest eigenvector. This is what tensor networks do, for example. But I can't hope to solve this in full generality because it's an exponentially large object. And one rigorous way to bypass this is to not ask precisely for all vector entries, but for these features, because they are numbers again. And this is some choice that I make to make sure that the problem is well posed. A polynomially scaling input and a polynomially scaling output. And the bottleneck is in between. Because how do we get from the classical description of these big matrices to quadratic functions or features of the smallest eigenvector? This is easy, but in the middle, how do we do that? The standard way is really to just do an eigenvalue decomposition, but this is expensive because the matrices in the middle are so big. And so maybe directly going from here to here is a very challenging problem. Tensor networks, for example, attempt to do that, and they can solve these problems under certain assumptions. And these assumptions are typically about the connectivity graph. And if you have kind of like a two-dimensional connectivity graph like here, tensor networks are not good, so they can't solve it. In fact, you can use known computationally hard problems like FreeSAT and encode it into this problem. So there's computational complexity obstacles that prevent us from believing that we can solve this problem in full generality. Okay, so what do? There's kind of like the traditional ansatz is tensor networks. You kind of like make assumptions on your problem class and then try to find a solution that works for these subclass of problems. And what we wanted to do is something else. We wanted to adopt a learning framework. What if we don't have to do the pipeline from input to output every single time, but maybe we have one family of these Hamiltonians, a fixed network configuration, in this case a hexagonal lattice, where only the couplings kind of like vary. And now I suddenly have a parametrized family of Hamiltonians and a parametrized family of associated ground state energies or features, okay? And there, the machine learning paradigm might hit in, where I can maybe learn from data. Don't do this in isolation, but really assume that maybe this is kind of like the type of family you're looking at, and you have access to 10,000, just a number I make up now, to 10,000 of these guys, where you already have labeled data in the sense that you have a parametrization of the original question, the Hamiltonian, and a parametrization of the associated ground state, labeled data. And I don't have to do that from scratch, but I can use this data here to train a machine learning model like a neural network in order to directly infer a classical efficient connection between the efficient input representation and the efficient output representation. Okay? So really use the power of data. And I'm really scared of math of deep learning. I know kind of like here in Vienna, we have some experts on that. It's a bit above my pay grade. So instead of really looking at a deep neural network, we make kind of like a trick, the neural tangent kernel that tells you that kind of like if the number of degrees of freedom in your network, kind of like the internal layers become very, very wide, then the trained neural network can be represented by a kernel interpolation. Basically a linear interpolation between the training data points you've seen already. Okay? And under this simplifying assumption, we can prove that this learning setting works. And for the remainder of this talk, I want to give you a high-level sketch, and we will not do it for the neural tangent kernel, which is mathematically a bit involved, but we will do it for something that's called the L2 Dirichlet kernel. And I don't know, I'm not a mathematician, but in my experience, it's often the case that if a math word looks very scary, like L2 Dirichlet kernel, it's actually an easy concept. It's the easy sounding words I'm afraid of, like category theory. But you will see that this L2 Dirichlet kernel is just a truncated Fourier series expansion. So it's really nothing deep. But for this toy model of a machine learning setting that learns from data, we'll be able to prove that this is possible. Under certain strong but reasonable assumptions on these Hamiltonian families, on these matrices, we can prove that these kind of like kernel methods really learn a classical function from new inputs to new outputs that achieves a small mean squared error when we only have access to a polynomial number of training data points and the runtime and memory for training the model and executing it is also polynomial. Under strong physical assumptions, you can prove that with access to data, you can actually solve this pipeline efficiently. Questions or comments at this point? There's a problem here. Maybe you see a problem. It's like, I hope the vision is clear, but there's one point that cannot work here. Yes? Yes. 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 No, but for me, the I in the Pauli Y is important because it ensures that the matrix is Hermitian. It ensures that the matrix is Hermitian, it's self-adjoint. Exactly. This is why I need the I. That's the only thing. Exactly. And we only ever have kind of like in our model Kronecker products of two of these Pauli Ys, and so the imaginary values cancel anyway. Good point. But here I emphasize efficiency and scalability. And at one point, I told you, what if we had access to labeled data? Here we have kind of like the description of the Hamiltonian, which is efficient. But here we have a description of the ground state. Not efficient, right? This is what I told you before. The ground state is an exponentially large vector. If I really insist on labeled training data of this form, I cannot ever be scalable. Okay? And this was one of the most important insights that I think our collaboration had over tensor networks. We used a new form of matrix sketches here. It is not tensor networks. But it's called classical shadows, and it's just kind of like a way of sketching, kind of like to low-dimensional, low-structure sketches of these very big ground states in a way that still allows you to infer the desired observables without needing to store exponentially large vectors. Okay? But for now, it's enough to see that this vision only makes sense if we have an efficient sketching way of presenting the ground states of the training data. And we found such a sketching procedure that is different from tensor networks and arguably easier to analyze. Are there more questions or comments at this point? Yes. Yes, it's a good question. And this is why the physicists themselves also have these summary parameters. They call it, I'm not good at that, but they call it, some of them measure correlations between individual spins. This gives you a big correlation matrix that actually tells you something about kind of like how the interactions work. Other features are magnetization, like do the spin points in the same direction? If they do, you have a magnet. And then there's also summary parameters for superconductivity and more fancy features. But this is kind of like really physics territory. I agree with you. Kind of like what would they do with an exponentially large matrix? But I can also tell you from experience that physicists often don't think about that. So. Excellent point. Okay. So what we kind of like achieved there is kind of like under strong assumptions on the Hamiltonian families, we can prove that you can actually efficiently learn the pipeline from a new description of such a Hamiltonian to a new ground state. And more recently, using ideas from L1 regression and compressed sensing, which I learned in this community actually, we managed to kind of like get this down from a quasi-polynomial scaling to a polylogarithmic scaling in the number of qubits. And the junior kind of like researcher on the project even pushed it down to constant. Kind of like there have been recent improvements in the complexity of these algorithms using ideas from compressed sensing to make it really scalable. Okay? So maybe very quickly, what do we need to prove that? And the first thing, I want to just quickly touch on it, is we need, in order to make sure that it's efficient, we need a way to sketch the training data. We need to sketch the vectors, the ground state vectors of Hamiltonians we've seen already. The data format that we use, and this is kind of like the insight we had from machine learning, is if these kind of like neural tangent kernels are linear interpolation schemes, we need a matrix sketch that is linear. Kind of like here, in this kind of like neural tangent regime, the output of the trained model for a new parameter is a linear combination of the ground states I've seen already. And I need a matrix sketch, if I want to use this and kind of like nicely work with that, I need a matrix sketch that is also linear. In the sense that I have a low dimensional matrix sketch of a big guy that ensures that the sketch of kind of like alpha times the first matrix plus the sketch of alpha times the second matrix is the sketch of alpha times the first matrix plus beta times the second matrix. If I have this, linear interpolation can work nicely with our matrix sketches. Okay? And this is a feature we found, a sketching method that does that. And traditional methods like tensor networks don't have this linearity property necessarily. We take a tensor network representation of one state and add a tensor network representation of the second state. It's possible, but not straightforward, to make sure that this is a tensor network representation with the same latent structure. Okay? So this is kind of like the main insight we had, and the formalism we use is basically Monte Carlo for big data. I don't want to go into details here, but we use importance sampling and Monte Carlo techniques to find Kronecker product sketches of these very high dimensional matrices. And Monte Carlo is linear, because probability theory is linear. So here is the main result. I quickly actually want to allude to a proof to, and it tells you that kind of like this learning pipeline can be done efficiently under certain strong assumptions. The first assumption we need is a constant spectral gap for all these parametrized matrices. It means that the smallest eigenvalue and the second smallest eigenvalue are separated by a constant. And so this avoids eigenvalue crossings, and this is important for stability. This is the mathematical assumption we need, and it's a strong assumption in the physical sense. And the other kind of like assumption we need, and this is necessary for our sketching, is that the observables or the features we look at have to be local. So kind of like we can look at correlations between pairs of spins, because they only affect kind of like two of these bodies, or magnetization, which is a sum of kind of like single body Kronecker products. We cannot look at complicated global directions. Okay, yes? No, just the smallest and the second to smallest. But for all possible parametrizations of my Hamiltonians. I now have a family. Yes. It has to be fixed throughout kind of like the parametrizations. No, exactly. I need a lower bound. Yes, exactly. But they can never come too close. And I guess like from matrix analysis, this makes sense for you, because the smallest eigenvalue vector is not stable if we have eigenvalue crossings. And this is how we avoid that. Yes, exactly. Yes, exactly. Yes. 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 I don't. I'm way more coarse there. Like here, what we really wanted to set out is that data helps. If you have access to enough data, your model, your interpolation model, will learn the symmetry and will kind of like use this. And I'm sure additional improvements are possible if you actually impose symmetry from the beginning. In our analysis, we actually don't need that. We just have access to data and a simple interpolation model, but this turns out to be enough to have a result like this. Yes. No. Yes. But here I don't even do that. It's kind of like really this machine learning mantra, just throw data at the problem and the model will learn it itself. Which is sad, but kind of like, it works way too well, I think. But I agree, kind of like this is a really kind of like superficial model. Let me quickly talk about the proof and you will see which direction we go. And you will maybe even see a potential for using symmetries, but so far we didn't. And yes, I agree. Yes, or the mean squared error as a figure of merit kind of like really makes the distribution important from which you learn, and this can hide interesting instances, but it also allows you in principle to find a distribution over interesting instances. Good point, Norbert. Okay? So basically, if we have a constant spectral gap for the matrices, it's a strong physical assumption, and the features we want to learn are not too complicated, like don't look at very, very intricate high-dimensional directions, but are also structured in this Kronecker product sense, then this works. And now, very quickly, what is the idea of the proof? And the first ingredient is just what we thought basic signal processing, but maybe it's not so basic. After all, because it's a weird non-asymptotic twist that we do. But kind of like here is a general theorem or proposition that all of you are probably more familiar than me. Consider a function from the m-dimensional Unicube into the real numbers and assume two things. The second thing is easier. Assume that your function is uniformly bounded in modulus. And also assume that the length of the gradient is also bounded by a constant everywhere. This means your function is not varying too quickly. Then random interpolation works. I can approximate the function by uniformly sampling in the Fourier domain and just interpolating the points, the function values at these points. Okay? This is what this says. And the way you do it is you use kind of like the fact that kind of like the gradient is controlled to go into the Fourier domain, do a Fourier series approach. Then you can cut off at a certain frequency because you have a band limited signal. Then the error remains controlled and you can do kind of like random interpolation using Monte Carlo, right? Oldest trick in your book, probably. Yes, exactly. But this is kind of like just kind of like the first idea in this direction. I think there's a lot of room for improvement. M is kind of the number of parameters that... No, this is controlled. This is polynomial. It's kind of the number of couplings that we have. And the one interesting thing we have here is, or maybe the one semi-interesting thing is the kind of like the number of sampling points we need only scales kind of like the M is down and kind of like the accuracy is in the exponent. Asymptotically, it would be the other way around. It would be kind of like accuracy to the number of degrees of freedom, I think. But here we kind of like have a non-asymptotic result where these two are switched. So the number of points we need only scales polynomial in the dimension, but it scales exponential in the accuracy. Which is probably weird for you, but you can do it now. Okay? But I already told you the proof, and you know it better than me. It's kind of like do a Fourier series ansatz, truncate in the Fourier domain, and then this L2 Dirichlet kernel emergence. I told you that this is a nice, kind of like an easy concept. It's just what you get when you do a truncation and go back. Not the best thing you can do here. I warned you in the beginning, if kind of like I do my job right, you will be unimpressed. On position to be unimpressed. But it tells you that kind of like interpolation is possible with a particular kernel function if the gradient of my function doesn't vary so much and the function is bounded in modulus. Right? And I guess there's no surprises here. No, I have no control. Exactly. The samples we absorb in this machine learning framework where we assume that we have a distribution over kind of like different Hamiltonians. And we sample from this distribution, let's say 10,000 test cases. This is my samples. And then I have to interpolate for the 10,000 first. Kind of like it's uniform sampling beforehand. I can't adaptively choose. Very good. So how can we relate this to the ground state problem I've been annoying you with for the last 40 minutes? Well, matrix analysis and a bit of perturbation theory. Kind of like what I just told you, and it's very familiar for you, if I have a function from the m-dimensional Unicube into the real numbers that don't vary too quickly and are bounded in modulus, I can kind of like efficiently learn it or interpolate it with random samples. This basically tells me that the machine learning framework works for such functions. Now, what functions do we choose? We choose the function that arises by taking a parametrization of a Hamiltonian, going to the associated ground state vector, and then evaluating a feature. And the feature is a Hermitian observable, so this is a real number. This is a function from parametrization of my big matrix to the one number, the feature of the associated smallest eigenvector. Okay? Function. And now, the properties of quantum many-party physics, the structure, the Kronecker product structure that emerges here, tells you that this function meets these requirements. Found in modulus is easy, because the smallest eigenvector is normalized. And a feature that I care about is also normalized in operator norm, and so kind of like the product between the two and the trace is also normalized. What is a bit more difficult is how can I make sure that the gradient doesn't vary too quickly? And here we really use the assumption of a constant spectral gap lower bound. Because kind of like these smallest eigenvectors are implicitly defined via the matrices they come from. And if we have a constant spectral gap, the matrix perturbation theory tells us if we perturb the matrices a bit, the smallest ground state space will remain stable. And you have to be very careful here because these are huge matrices, but this assumption of a constant spectral gap, together with the locality that tells you that the Kronecker products of a new guy cannot affect too many of these factors, gives you some sort of locality, and together this allows you to prove that these functions cannot vary too quickly. Okay? It's really matrix perturbation theory and the strong assumption on a constant spectral gap. But with this, we are now almost there. The elementary sampling result from signal processing with this L2 Dirichlet kernel, which is just truncated Fourier series approximation, allows you to also predict these ground state features if the associated family of Hamiltonians has a constant spectral gap lower bound, and the features we care about are kind of like structured and localized. Okay? Now we're almost there. The only thing that is missing is that in this formalism, I kind of like interpolate an exact new, a learned candidate for a new ground state vector by linear interpolating existing ground state vectors exactly. So this is not efficient yet because it interpolates exponentially large vectors. And the last thing I need is to sketch these. Because we have now kind of like an exponent, kind of like a quasi-polynomial learning algorithm here. And so the last step is really data compression via matrix sketching. We have to find efficient sketches of these big matrices that we can interpolate them and to get an efficient sketch of the new matrix of the new candidate Hamiltonian. And I already alluded to that. The problem is now we have kind of like a linear combination and interpolation of existing ground states, but they are all exponentially large, so we need to compress. And one way is to just directly compress to the features you care about. This is something you can do. But what we chose is kind of like a more expressive sketch that is linear and captures the latent structure. And what we do is really Monte Carlo for big data. We kind of like try to represent these kind of like big correlated matrices as a probabilistic average of elementary Kronecker products, and then we can store the elementary Kronecker products and solve the curse of dimensionality. And again, this is where we deviate from existing approaches that use tensor networks, because with tensor networks, we don't have these nice linear interpolation results off the bat. And this would be an obstacle to prove kind of like our results for tensor network representations of ground states. But this is just matrix sketching. And with this, we're done. Signal processing gives us kind of like an interpolation result with random sample points that scales quasi-polynomially in the dimension of kind of like the function space, in the dimension of kind of like the pre-image space. Matrix perturbation theory allows us to convert the physical assumptions from quantum many-body physics into stability of the smallest eigenspaces of these matrices. And this tells us that the associated functions, the features parameterized by the Hamiltonians, are not too quickly varying functions. So we can use linear interpolation. And the last trick is matrix sketching to make sure that we never store exponentially many floating point numbers in an array. Okay. And just very quickly, these things don't only work in theory, they work way better in practice. Like this is numerical studies we did with Amazon Web Services. It pays off to have a friend at Amazon Web Services because they have a lot of cloud computing time you can fry. And this is this 25 spin example that I mentioned earlier. So the underlying problem is really 2 to the 25 dimensions. So kind of like a brute force search is not so easy, but our friend at Amazon did it. And here you can really see one possible configuration where we randomly chose the thickness, but specified it. And now this is the one Hamiltonian we care about. What you here see is the exact correlation matrix between the individual spins in the ground state. So this tells you how correlated is the ground state configuration. The correlation matrix, n by n. And in order to get there, this took time. Because 2 to the 25 is a big number, and if you want to get good approximations, this really required Amazon Cloud Computing time. And what you can see on the right-hand side is, I mean, it's visually not so easy. It looks very similar. It's a bit different. This is the result from our interpolation. Where we kind of like used our friend at Amazon Web Services to fry kind of like the servers 10,000 times to get training data points. And then we inferred a classical easy function for new data points, and we evaluated it for this test case. Yes? I agree. I agree. I agree. You're right. Thanks for making this. I didn't make the plots since you last made the complaint. Yet. So good that you're here again. Just what I wanted to say is, no, really, kind of like this is a very simplistic model, but the main result is kind of like the mathematical framework, and this is just kind of like a empirical confirmation that could be done much more thoroughly. And then we did it for kind of like more involved models with newer actual machine learning techniques like graph neural networks, and it works better. Like this is really just the most basic idea that we had, but if you use actual state-of-the-art machine learning techniques, you get better empirical prediction, but I have no idea on how to make proofs there. And we looked at other physical systems as well. And with this, I'm done. Thank you very much for paying attention, and thank you very much for being so interactive. I really appreciated each of your questions, and I hope that I got at least some physics jargon across. What was our ambition? We wanted to provide rigorous theory support for an efficient and fruitful synergy between, let's say, quantum computing or quantum experiments. This is where quantum many-body physics comes from, and machine learning for classical computers on the other hand. This is kind of like a very hypey topic. A lot of people work on this, and we wanted to at least provide some theoretical support that this can be a fruitful combination. And the concrete objective we chose is to learn how to predict these properties of many-body ground state systems, because this is a very well-defined mathematical problem that features prominently in condensed matter physics. And the result is maybe not so surprising. Under strong assumptions of the physical systems in question, we can prove that this works efficiently in the sense of quasi-polynomial theoretical performance guarantees. And the actual constructive proof combines 3 ingredients, and each of which is easy for experts. First, basic signal processing, approximate a slowly varying function by uniform sampling. Like this is where you are the experts. The second part is kind of like many-body physics and matrix perturbation theory. Can you connect these basic results to learning these types of latent structures in big matrices? And the answer is yes, with matrix perturbation theory. And the third part, which was maybe the reason why we succeeded there, is you need a good way of sketching the matrices to make sure that you never have to store strings of exponentially many numbers. And there we use this Monte Carlo technique for efficient and linear data compression. And then maybe I should mention that this was the first work of many, and we iteratively refined proof techniques to improve the cost, basically to first logarithmic in the system size, and now Laura Lewis, kind of like a really fantastic young PhD student, even mentioned to get a constant, kind of like a number of samples that only is independent of the size of the system. And the numerical experiments, they are not above scrutiny, but they at least kind of like highlight that these ideas really work in practice. Thank you very much for your attention. Here is a team slide, because many of you maybe kind of like usually drive past Linz without stepping off. We kind of like highlight that Linz is actually an interesting city where you can get off the train and, for example, visit our group. We kind of like exist for 1.5 years now. And I think it's a number of fantastic colleagues, Johannes Kofler most notably. And I'm really proud we're working hard to get the next speaker affiliated with our group as well. Thank you very much for your attention.